Hey everyone, welcome back to Abstract Algebra 1. This will be part B of Lecture 6. And where we left off, we had just proven a theorem related to, let me write down what we just proved. The theorem we just showed said that A is an element of a group, and the order of A is n. Then for k, a positive integer, the group generated by a to the k is equal to the group generated by a to the GCD of n and k. And the order of the element a to the k is equal to n over the GCD of n and k. Okay, so we just finished proving this theorem, and there's a couple of quick corollaries that kind of follow off of this one. There's one main kind of follow-up theorem, then a couple of cases that are so commonly used that we generally call them out, right? And so the quick corollary here is that if we let the order of A equal n, then if a to the I, the group generated by a to the I, is equal to the group generated by a to the j, well, this is true if and only if the greatest common divisor of n and I equals the greatest common divisor of n and j. Okay, so this is the theorem, right? So if I've got an element A in a group, I kind of skipped that part, but you can imagine A is in a group, some element in a group, it has order n, then these two groups are the same if and only if the greatest common divisor between n and I is the same as the greatest common divisor between n and j. Okay. All right, so this one is fairly easy to prove. The previous, we wrap in the result from the previous theorem here to make the proof really quick. So the previous theorem, which of course, if you're jumping into just part B of the lecture, you should definitely go watch part A because that one's important. So the previous theorem showed that, what did it show? It showed that a to the I was equal to a raised to the GCD of n and I. And of course, the same thing for the j group. Okay, and so we showed this. So really, the proof of this theorem reduces to basically a to the GCD of n and I equals a to the GCD of n and j if and only if GCD of n comma I equals GCD of n comma j. Right, so basically just the fact that this piece here, right, from up here, can be replaced by this, and this piece here can be replaced by this, allows us to use this expression for this group in the proof of the theorem, right, which is quite a bit, makes the theorem extremely easy to show. So we can go the one direction first, right? So assume that the GCD of n comma I equals the GCD of n comma j. Well, then certainly if I take a and I raise it to these two powers and they're equal, then I get what I want. Right? Right, so that's kind of obvious, right? If these two exponents are the same and the bases are the same, then clearly the groups are the same. That part's really straightforward. The other part's pretty straightforward as well. All right, let's go the other direction. Let's assume that a to the GCD of n comma I equals a to the GCD n comma j. Okay, and what does that imply? Well, it implies that the order of these two elements is the same, right? We know that the order of this group is the same as the order of the element that generates it, right? So that implies that the order of a raised to the GCD of ni equals the order of a to the GCD of nj, right? And of course, by the previous theorem, this implies that n over the GCD of n comma I equals n over the GCD of n comma j, and of course that implies that the denominators are the same. And that's it for this one. So you can see it's very straightforward. The fact that we can just swap out this group for this group that has more information makes the proof really quick. Really quick. Now, there's a couple of special cases of this theorem that get used so frequently that we like to just call it out. It's really the same theorem, they're just special cases. So I'm going to write them out here. And we're not going to prove these theorems, but I think you'll see that, well, they're really just a special case of the last one. So we're going to let G equal A, so it's a cyclic group generated by A. So we'll let G be a cyclic group of order n. Okay, it's a cyclic group of order n. Then G is equal to the group generated by A to the K if and only if the greatest common divisor of n and k is 1, meaning n and k are relatively prime. All right. Okay, and then the other one, which is very similar, an integer k in z to the n, z sub n, cyclic group, is a generator of Zn if and only if n and k are relatively prime again. Right? So if n and k are relatively prime, then you get the whole group back. Okay. So in both cases here, so G is a cyclic group of order n. So it's generated by A. It's also generated by A to the k if n and k are relatively prime. Right? And we'll see a great example of this one right here. Same thing is true here in Zn. This is an additive group. If integer z or an integer k in Zn is a generator of Zn if and only if, again, relatively prime. Let's see an example of these two, and this will be also serve as an example of the big theorem prior to this. Okay, so to see the power of the theorem, let's use them to find all the generators of the big cyclic group U50. So we're going to consider U50. Okay, I'm not going to list all the elements of U50, but again, this is multiplication mod 50, right? But I'm not going to list all the elements, but it can be done. And if you do this, you'll see that the order of U50 is 20. There's 20 elements in U50. All right, and then one of the things you'll be able to see also is that 3 is a generator of U50. Okay. So the theorem says, what does the theorem say? It says that if the order of the group is n, then G is equal to the group generated by A to the k if and only if the GCD of n and k is 1, right? So n and k are relatively prime. Okay, so which integers, so in our case, the order of the group n is equal to 20. So which integers are relatively prime to 20? Right, so n is equal to 20. Our k's we can choose from 0 to 19, basically. Right, so which ones work, right? You can kind of go through this list. And so what you would see is that 1 is relatively prime to 20. 2 is not relatively prime to 20. They both have a common divisor of 2. 3 is relatively prime to 20. 4 and 5 obviously are not relatively prime. They divide 20. So neither is 6. It's divisible by 2. So the others are 7 and 9, 11, 13, 17, and 19. So these are all the k where the GCD of 20 and k is 1. Right, now you could go above 20, but then you would end up just kind of repeating yourself, right? Okay. So then the generators here, the generators of G are, well, I should say of U50. The generators of U50 are based on these. Okay, so for example, 3 to the k equals 3 to the 1. Mod 20 is 3. So 3 is a generator. 3 to the k equals 3 cubed. Mod 50, not 20, is equal to, well, 3 times 3 is 9, times 3 is 27, so this is equal to 27. So 27 is a generator of U50. Right, and so on. And I can just go down the list, 3 to the k, right? The next one would be 3 to the 7th, then 3 to the 9th, 3 to the 11th, 13, right, and so on. And so the last one on the list would be the 3 to the 19th here. So 3 to the 19th power mod 50. Well, it turns out you can plug that in. It's a gargantuous number, but it turns out that that's equal to 17, right? When you identify the least residue there, and it's 17. Right? And so all of the generators of U50, I've got the list here, all of the generators are, you get the 3 and the 27, and then everything in between would be 37, 33, 47, 23, 13, and 17. Right? And these are all based on the k's, which are these guys, 1, 3, 7, 9, 13, 17, 19. Okay, respectively. All right, so you can see how powerful this is, right? So you can figure out what all the generators are, what all of the a to the k generators are given an a for any cyclic group. All right, very good, very good. The next theorem is kind of the big result, well, one of the bigger results in cyclic groups. It's actually called the fundamental theorem of cyclic groups. And we're not going to be able to prove it just due to time. It might take 45 minutes to write the proof out, but I'll state it and we'll see what it's about. So the fundamental theorem of cyclic groups. Okay, and so what does it say? Well, it says every subgroup of a cyclic group is cyclic. Oops, cyclic. Every subgroup of a cyclic group is cyclic. That's the first statement. All right, so that's the first part, right? So if I have a cyclic group and I identify a subgroup of the cyclic group, it's automatically cyclic. Okay, so that maybe is something that you would expect. That might be not unexpected. What else is there? Moreover, if the order of a subgroup generated by A is n, then the order of any subgroup of A is a divisor of n. It's a divisor of n. And, right, for each positive divisor, k of n, the group A has exactly one subgroup of order k, right? Namely, the subgroup generated by A to the n over k power. Okay, that's the theorem. Really interesting theorem, lots of structure here. Right, so the first statement is easy. Every subgroup of a cyclic group is cyclic. That part makes pretty good sense. Second statement says that if the group generated by A, cyclic group generated by A, has order n, then the order of any subgroup of A has to be a divisor of n. That's deep. Okay, so any subgroup of A, the cyclic group A, has to divide the order of the main group. The order of, of the subgroup has to divide the order of the main group. Okay, and it says for each positive divisor, k of n, so k is a divisor of n, for every positive integer that divides n, the group A has exactly one subgroup of order k. Right, and it is of course going to be the group generated by the element A raised to the whatever the result of the division is, n over k. Beautiful theorem. Beautiful theorem. As I said, the theorem is, I don't think that the proof is too difficult. It's just time consuming, and this lecture is already going to be pushing 2 hours. So I won't prove it, but it's one you should look up. It's definitely one you should look up. It's a deep and interesting proof, and you should look it up. It'll be very easy to find examples of the proof on the internet, and so I will leave it up to you. But let's see an example of this theorem in action. Okay, we're going to consider a cyclic group A. Okay, and we're going to say that the order of A is 30. Okay, so there's 30 elements in this cyclic group. Okay, then we could list out we could write out the complete list of subgroups of A. We could write them out. Right? So the first one, of course, is A itself. We know what that looks like. It's A squared, dot, 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 A to the 29th power. Right? We know that that's A itself, which is technically a subgroup. Okay. Now, think about what divides the order of the group. The order of the group is 30. What divides that? Well, 2 divides it. Okay, so that means A squared is a subgroup, right? And what are the elements of that? A squared, A to the 4th power, all the way up to A to the 28th power. Right? Now let's put on here the order of these things. So the order of this guy, we know this is the whole group, so it's 30. What's the order of this got to be? Well, it's n over k, isn't it? It's n over k. I'll write it here. So it would be 30 over 2, which is 15. There'd be 15 elements in there. That's pretty clear. What about the next divisor of 30 would be 3. So a cubed is going to be a subgroup. E, a cubed, a to the 6th power, and so on, all the way up to a to the 27th power. And the order of this group, subgroup, again, is n over k. In this case, it's 30 over 3, so you're going to have 10 elements in here, and so on. You could keep going. And basically, you're going to have a subgroup for every divisor of 30. So you'd have, we did 2 and 3 here. You would also have subgroups for 5, 6, 10, 15, and 30. And what you should do is you should go prove, you should take a couple of these examples, maybe take this one, and just show that indeed there is closure here. Right? So for example, a to the 30th, we'll do a to the 15th. That's going to be equal to a to the 15th, and just those two actually. Right? And the order of that guy is of course equal to n over k, which is 30 over 15, which is 2. Right? 2 elements there. All right. And then a to the 30th would just be the identity. I guess I can put that on there, just for completeness. Okay. So these are all of the subgroups of this cyclic group. So in general, if A has order n, and if k divides n, then a to the n over k power is the unique subgroup of order k. So if the order of A is n, and if k divides n, then a to the n over k is the unique subgroup of order k. Okay, so that's basically what these theorems say. Now again, I highly encourage you to go out and walk through the proof of the fundamental theorem of cyclic groups. It's deep, it's interesting, it's obviously powerful, and it's accessible. It just takes a little too long to get into here. Okay, now we've got just a couple more theorems that I want to talk through quick. It'll probably take a couple minutes is all. But the last 2 theorems will actually draw from from a function that you would see if you took a number theory course, but you may not have. So this is what's called the Euler phi function. Relatively easy to understand, comes up in all over the place in mathematics. And so for the Euler phi function, we let phi of 1 equal 1. And then for any n greater than 1, phi of n denotes the number of positive integers less than n, but relatively prime to n. It denotes the number of positive integers less than n and relatively prime to n. Okay. All right, so let's write a couple of these out. So if I have my n and my phi of n, okay, so like just do 1 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, we'll say. So again, phi of 1 is defined as 1. Phi of 2 would be 1, because the only integer less than 2 that's relatively prime to 2 is 1. Phi of 3 would be 2. Both 1 and 2 are relatively prime to 3. Phi of 4 would be 2. 1 and 3 are both relatively prime to 4. Phi of 5 is 4. Basically, 5 is a prime number, so everything smaller than it is relatively prime to it. And phi of 6 is 2, phi of 7 is 6, phi of 8 is 4, phi of 9 is 6, and phi of 10 is 4. Right? So what are the 4 positive integers relatively that are less than 10 but relatively prime to 10? So it'd be 1, 3, not 4, not 5, not 6. 7 is relatively prime to 10, and 9 is relatively prime to 10. Right? So this one would be this set here. Right? So relatively prime again just means that the only means that the greatest common divisor is basically 1. Okay, meaning that there are no non-trivial divisors of the two numbers. Okay. All right. So one thing to notice, and this is interesting because we've been using this example this whole time, if u of n is the multiplicative group order n, then the order of un is phi n. So I'm not going to go through that derivation, but I think you can think this through and figure this out. Right? So for example, u of 10 that we've been using a lot, 1, 3, 7, and 9. This is just a list of the 4 values that comprise phi of 10. Okay, so that is exactly where that comes from. Okay, 2 quick theorems, right, to wrap this section up. This is a difficult section, I think. You're going to go kind of deep on cyclic groups. So if D is a positive divisor of n, if D is a positive divisor of n, then the number of elements of order D in a cyclic group of order n is phi of D, right? Just basically taking our U10 example and expanding it, saying, oh yes, indeed, right? So if D is some positive divisor of n, if D divides n, and the number of elements of order D in a cyclic group of order n is phi of D. Right? We can prove this one pretty quickly. This one comes pretty quick. So by the fundamental theorem, there's exactly one subgroup of order D. By the fundamental theorem, there is exactly one subgroup of order D. And we're going to call it, in this case, A. Okay. Then what? Every element of order D also generates A, right? Every element of order D also generates A. And an element A to the K generates A if and only if, we saw this, the GCD of n and k is 1, right? And the number of such k's, how many are there? Well, there's phi of D. Right? The number of such k's is exactly phi of D. That's the definition of the thing. Okay, and so that's the proof. It's kind of wordy, but you can go back and fill it in if you like. Now, this is actually a pretty surprising result if you think about it. It basically says that given a group of order n, the number of elements of order D depends only on D, right? Right, so given a group, well, let's say this, given the groups like Z8, Z640, and Z80,000, we'll say, three very different groups, right? Mod 8, mod 640, mod 80,000. Now, all three of the order of these groups are, of course, 8, 640, and 80,000, right? So N is 8, 640, and 80,000, right? And so so consider the elements of order 8. How many elements of order 8 are in each of these? Well, you might think that Z80,000 has more elements of order 8 than Z8 does. You would be mistaken, right? Phi of 8, we saw already, is equal to 4, right? Phi of 8 is equal to 4. That's how many elements of order 8 are in all three of these groups. 4 there, 4 of them there, and 4 of them there. So only 4 elements in each of these groups of order 8. This one has 80,000 total elements. 4 of them have order 8. This has 640 elements. 4 of them have order 8. That's what the theorem basically says. Okay, so pretty surprising theorem, but very interesting also. All right, so I think we'll probably end it there, and when we come back, we'll get into a different kind of group, a group called a group of type known as permutation groups. Right? And so that'll be next time in the next lecture. So we'll get into permutation groups next, and until then, take care, and we'll see you.